This is a video about smooth analysis. Smooth analysis was a collection of definitions and theorems, and we believe that it would help us better understand the simplex method, an algorithm which is fast in practice, but in a way that theory has been struggling to explain. My name is Huiberts, and in this video I will describe exactly what smooth analysis was, what we as a theoretical computer science community hope to achieve by studying it, and what we actually achieved. The simplex method is arguably one of the most important algorithms in the world. It's used to solve linear programming problems, which in turn means it's used for everything that builds upon linear programming. Today, we will model the simplex method as follows. As input, we receive a convex polyhedron, given as a set of linear inequalities. We also receive a linear objective function. With that input, we have to maximize the objective function over all points inside the polyhedron. What the simplex method does is as follows. At first, it knows any vertex of the polyhedron, and then it can make these moves that are called pivot steps. In a pivot step, the simplex method chooses one of the edges that is adjacent to its current vertex, and it moves itself to the other endpoint of the chosen edge other than the one it was just at. A simplex method will keep making these pivot steps in such a way that after every step, the objective function is typically higher than it was before. After some number of steps, it will find a vertex where the objective function is maximized, and at that point, we can output that vertex that we just found, and we're finished. Now, what's most interesting right now from a theoretical perspective is to ask how many of these pivot steps will be taken before an optimal solution is found. If the number is small, then the algorithm is fast, and if the number is large, then the algorithm is slow. Turns out, in practice, the number of pivot steps required is roughly linear in the dimensions of the polyhedron. That is our observed ground truth. This is the knowledge of over 75 years of anecdotes, and it is even mentioned in the FICO Express user manual. Now, our goal is to use theorems and proofs to understand why the simplex method is fast, why the number of pivot steps is this low. The first attempt to understand the running time of the simplex method was through worst-case analysis. Starting in the early 1970s and continuing to this day, we've seen a lot of results that actually show that the worst-case complexity of different variants of the simplex method is superpolynomial or exponential. That is, according to worst-case analysis, the simplex method is a slow algorithm. So if we want to understand why the simplex method is fast, then worst-case analysis might not be the right tool for us. A second popular approach that came up recently after was average-case analysis. This started in the late 70s and continued till the 90s, where people proved that different variants of the simplex method and different probability distributions over the random inputs, for those they proved that the expected running time is bounded from above when sampling these random linear programs from these probability distributions. The community got very good at producing these types of theorems, but there was a creeping doubt about their value for the scientific cause. Because, you see, real-world linear programs are structured in very meaningful ways. For a visual analogy, we might think of a real-world photograph having all kinds of recognizable shapes and objects. But randomly sampled linear programs, they are structured in a very different way. That is, with its own very recognizable features. In the visual analogy, we can think of a random bitmap image, which looks very distinct from any typical photograph. So, typical objects and random objects are very different from one another. People came to realize that just because you're studying the latter doesn't mean you're learning anything about the former. And so, it was time for something new. Enter smooth analysis. The definition of smooth analysis started with an adversarially specified inequality form LP. That is, maximize C transpose X subject to A bar X less than equal B bar. We would assume that the rows of the extended matrix A bar B bar each had norma at most 1 in order for the rest of the definition to make sense. Then we would assume that every entry of the constraint data would get independently and normally distributed random noise added to it. So we would sample A hat and B hat with IID Gaussian entries, and then the smooth analysis of a simplex method would be measured as we take the maximum over A bar, B bar, and C of the expectation over A hat and B hat of the number of pivot steps it takes a simplex method to maximize C transpose times X subject to A bar plus A hat X at most B bar plus B hat. When Dan Spielman and Cheng-Hua Tang first published this definition in 2001, they also demonstrated that a simplex method existed for which this quantity was provably bounded from above. Specifically, they managed to prove that the smooth complexity of their simplex method was at most order n to the 86 times d to the 55 times sigma to the minus 30, where n is the number of inequalities, d is the number of variables, and sigma is the standard deviation of the noise, assuming sigma is small enough. And this type of polynomial dependence on n, d, and sigma was what they were hoping for. Now, of course, we know that everybody likes a good definition, and so soon enough there was a bit of a competition of people proving stronger and stronger upper bounds. All these results had these 3 parameter dependencies on d, on n, and on sigma, but for a variety of reasons, one of which involves the AMGM inequality, it has made sense to only really work to improve the dependence on the noise parameter sigma. So let's plot the progress in reducing this polynomial degree. The first result, by Spielman and Tang, their proof consisted of 2 parts. There was a geometric estimate bounding the expected complexity of a quantity that we now know as the shadow size, and an algorithm whose running time could be bounded as a function of the shadow size. And these 2 parts together would give you an upper bound on the expected running time of the algorithm. This 2-part structure was well established already from the average case analysis literature, but the technical effort required to make it work for smooth complexity was substantial. Spielman and Tang's upper bound on the smooth complexity for the simplex method clocks in at sigma to the minus 30. Just 4 years later, Dan Spielman came back, this time working together with Amit Deshpande to cut the polynomial degree for sigma by a factor of 3, thus improving it to sigma to the minus 10. Their improvement was entirely due to a better analysis of the shadow size, which they obtained using somehow a completely different route than had been used in previous results. The next improvement happened in 2006, when Roman Verschinnen came on the scene. He worked on 2 fronts, finding both a greatly improved algorithm and a stronger bound on the shadow size. What's interesting is that Verschinnen followed the shadow size analysis route of Spielman and Tang almost the entire way, except that Verschinnen realized that the most difficult section of the Spielman and Tang analysis just could be skipped entirely. Since every additional probabilistic estimate comes at a cost in the running time, when Verschinnen bypassed this last part of the analysis, it resulted in a major time save. However, the bulk of Verschinnen's improvement actually did come from his better designed algorithm, which allowed him to more efficiently reduce the running time to a shadow size. Together, these 2 improvements brought the total time down to sigma to the minus 4. This is where the smooth complexity of the simplex method stood for over a decade. Despite Verschinnen having simplified the Spielman-Tang analysis greatly, the area continued to have a reputation for great difficulty, and so there was not a lot of animo to improve this soon. The first progress happened in 2018, when I worked together with Daniel Dadouche to clean up this smooth analysis result. In hindsight, I would describe our work as us taking Verschinnen's shadow size theorem, reinterpreting what his analysis did, and then rewriting a completely new proof that did the same thing but in a different technical matter. Our paper got very good reception, I think primarily for being easier to understand, but that wasn't all. Like, in the work of Despande and Spielman, we found an important insight about what I'm going to call the effective log-Lipschitz parameter of the Gaussian distribution. And by adding that insight into our analysis, we were able to cut the exponent in half. So doing this, we got the running time down to sigma to the -2. This started a new period of active progress. The next improvement I want to mention is a 2023 paper by Yinta Li, Xinqi Zhang, and myself. We noticed that there were these two completely different strategies for studying the shadow size. There was the approach used by Spielman, Teng, Verschinnen, Dadouche, and myself, and then there was the approach of Despande and Spielman. Both were based on potential arguments, where you have a fixed amount of potential function available, and any pivot step would eat up, on average, some fixed quantity of that, and because the total available potential is bounded, that would give you a limit on the expected number of pivot steps. But the two approaches differed in which potential function they considered. So what we did in 2023 is we figured out how to combine these two arguments. If a pivot step ate up a small amount of one potential function, then it would necessarily eat up a large amount of the other potential function. So now, that was in principle a nice plan, but execution proved difficult. We ended up having to revisit a lot of the old strategies from the 2001 paper by Spielman and Teng, and we lost a lot of time there. Still, the two potential route was enough to shave off a little bit of time, so our total time clocked in at sigma to the -3/2. And that brings us to the present, to this paper from 2025 by Elian Bach and myself. While working on the replacement for smooth analysis, together with two more collaborators, Alex Black and Sean Kaver, we happened to strike algorithmic gold. While that project was stuck in a bit of a slow phase, Elian and I punched out the application of this new algorithmic technology to smooth analysis. And what was that algorithmic innovation? Well, it was really to randomize the pivot direction choosing procedure, the pivot rule. By choosing the edge according to the correct probability distribution, we could offload some of the work in the shadow bound from the randomness in the data to randomness in the algorithm. And because we had less dependence on the randomness in the algorithm, this was somehow enough to skip an entire section of Spielman and Teng lemmas that we required in HLZ. And so together this resulted in a lot of time save. With this new algorithm and shadow size, the current best smoothed complexity of a simplex method stands at square root of 1/sigma times dimension to the 2.75 times polylog number of inequalities. And realistically, this is where the sigma dependence will stand forever. We found that we could adapt a lower bound construction from an average case analysis paper written by Gilles Bonnet, Daniel Dadouche, Uro Grupel, Galina Lifshitz, and myself to show that square root 1/sigma, polylog 1/sigmas is best possible. Now that we know what the results are, there are only two things left to discuss. What did we believe that smooth analysis was good for at the time, and what do we think in hindsight that we learned? Depending on who you asked, different reasons would be given as to why we studied smooth analysis for the simplex method. One common interpretation is as an interpolation between worst case analysis and average case analysis. The thinking was that worst case analysis was good in that it accommodates for arbitrarily structured inputs, but bad because the predicted running time was too high. Average case analysis, people would say, has the opposite problem. The inputs were thought to have too particular of a structure, the random structure, which we thought led to the predicted running times being perhaps too low. With these two endpoints, then a spectrum naturally proposes itself. If we interpolated between one model with too high of a running time and one model with too low of a running time, then surely an interpolation would be in the Goldilocks zone of good running time guarantees. This interpolated model is smooth analysis, and it was somehow thought to combine the strengths of adversarial large-scale structure with the necessary randomness on the small scale to grant meaningfully strong running time guarantees. This was, however, not the only argument for smooth analysis that we believed in. We used to say that the random Gaussian noise, that it actually modeled some specific aspect of the input data. But whether we modeled measurement error or numerical error or various arbitrary influences was never really discussed. At other times, we would say that the noise modeled actually the numerical effects in the computer that make it hard to reproduce worst case behavior in actual code. I think that we kind of had an unspoken agreement to not question the details all too much. The theorems didn't care about what interpretation they had, so we felt no urge to restrict ourselves to any fixed position that someone could disagree with. Whatever the interpretation though, there's no doubt that we all really believed in the explanatory power of this framework. Spielman and Zheng, they won the Gödel Prize for their work on smooth analysis, the definition and the first result. The prize committee wrote that smooth analysis provided a rigorous framework for explaining the practical success of algorithms. Now, all jokes aside, smooth analysis for the Simplex method was a resounding success. It provided people with the opportunity to learn and develop so much interesting new mathematics. And since all of this new math is shaped like analysis of the Simplex method, some of it continues to be useful even now that the days of smooth analysis are behind us. The only reason that we were able to invent a successor is because we knew all of these proofs, we knew the flaws, we knew the strengths. What's perhaps even more important is that the game of proving and publishing ever stronger smooth analysis bounds, it provided a viable career path into Simplex method research. I believe that the existence of this path is part of the reason why the field has seen such a resurgence of interests, with many young people getting into this line of work now. And yeah, that's it. That's it for me. Thank you so much for watching. See you next time.